Okay, so good morning. And in this class, we will look at the backpropagation algorithm. The context to it is, as we discussed in the previous classes, so far we assume that we somehow get the line that separates. And then in the last few classes, we studied how you could perform nonlinear classification, particularly when you cannot separate just by a single plane, hyperplane. So we have seen that you could use multiple neurons instead of a single neuron, and that's, you call it as a hidden layer. Not only that, we have seen that it need not be a single hidden layer, it can be multiple hidden layers. Okay, and just one more point to be added to that is, even your output layer in general can contain multiple neurons sometimes, and then you may take a call if you want, means to be keep it general. Even you keep, let's say you want to look at what is the probability of a given sample to belong to each of the classes, for example. That case, probably you don't want to use a single neuron and get only one output. Rather, you would like to say that, let's say with 40% probability it belongs to class A, and 60% probability with 60% to class B, or it could be even more classes also. Okay, so in all our workout today, what we will do is we keep that also in general, not necessarily keeping one neuron at the output. And the objective here is, I have taken a particular configuration of your network, so many number of hidden layers. In each layer you have fixed the neurons, and now you have a set of inputs. Now with giving these inputs, you will get some output. You know in the training data set what the output to expect. Now, depending on the difference between the expected output versus the output actually you are getting there, how do you modify all these weights till the other end so that finally you get a classifier that does in a desired manner? So that is the objective here. As you could see here, you look at the output, and from there you backpropagate some certain things there. So that's why we also refer to it as backpropagation algorithm. Okay, so what I will do now is I will draw two layers of neurons. I will call it as R layer and R plus R minus 1 and R layer, and we'll work out for these two among all those things, and this R then can vary from the first layer to the last layer. Okay, that is how we will do it. So let me draw a couple of layers here. There is a hope you would realize now why I'm separating now the summation from the activation function, because we need to take derivatives and all. So the way we need to deal with them is different. So that's why, contrary to the way I have shown you guys in the previous class, I am now separating the summation from my activation function. So I call this as some activation function F. Okay, and I do have an output there. Similarly, you may argue, why should I take same activation function? No, but for now we take the same. That doesn't really change any of things for you. Okay, so let me call this as R minus 1 layer, and next to that I have R layer. So this is the first layer, second layer, or this is fourth layer, this is fifth layer. So what I do a similar stuff here. Right. Again, number of neurons in each layer could be varying, right? So let us assume that there are L layers. There are capital L layers, and the number of neurons in that particular layer be given by in a R layer number of neurons in that be k subscript r. Okay. And r minus 1 is k subscript r minus 1. By writing and in a hurry, don't think that you are substituting kr minus 1. So r minus 1 is in your subscript you are using for r minus 1 layer. Okay, so that also we keep it as a variable parameter. Now what could happen? So I hope you already have noticed that the bias I have already absorbed into one of those weights. That's why I'm not keeping here anymore the bias here for the summation. Say, let me draw it for one of them here. So of course, you will draw in the same way for each of them, just to not crowd it too much and finally not able to see the variable name itself. I'm just drawing it for one. So for each of these layers, the input will come here. Similarly to each of them, and this will continue. Now, looking at this, and also I'm telling you that in a layer capital L, in a layer rth layer, number of neurons is kr. Okay, k subscript r, that I have given you. First question for you: what would be the size of your w vector here in this case? For, let's say, what we will do now, I need to write, I am now interested in the, finally I need to find out this w vectors for each node. Okay, now I need to deal with layer, in which layer it is. Okay, so for example, if I am interested in the r layer, so I will keep the layer number as a superscript here. That is not good enough. In each layer there are, for a rth layer, there are k subscript r number of neurons there. So each will have a weight matrix, weight vector, right? So this I will keep here j. So it is telling you in the jth node, okay, of the rth layer, for that particular neuron, what is the weight vector? It's a vector. So let me also keep a bar here. Okay, I'm keeping now vector size a bar reduced so that superscript and subscript can come comfortably sit there. What would be the size of this? Can you tell me? Right. It is from the all neurons from the r minus 1 layer, it is getting the inputs. Hope I'm clear. So that size will be, number of neurons there will be k subscript r minus 1. Is that enough or something I have to add? For the weight vector? Plus 1. Because of bias term, which I have not writing it separately. Am I clear? Correct. In each layer, no. This is the layer number. So here there are k subscript r minus 1 neurons are there here. Say that number I am denoting with this, okay, symbol. Here there are k subscript r neurons are there. So obviously the weight should come from each of them, right? Plus 1 for the bias. Am I clear now? Right. So suppose if I want to, finally I need to adjust the, you start with some random weights and you need to adjust those weights, correct? So w subscript j superscript r bar of nu will be equal to wj r bar of volt, okay, plus some delta w bar j r. So this is telling you the adjustment you need to do for that. Yes. What is? Yeah. See, there are L layers. What does that mean? This is one layer. This is one layer. You could have so many, there are L layers are there. In each layer, there could be different number of neurons. For a layer number, as a subscript to k, I am denoting the number of neurons in that layer. Is that clear? Good. So now you see here. Now, in general, in a rth layer, for a jth neuron, it has a set of weights. You start with some initial value and you iterate over it. And That's why you need to find out at each iteration this delta W that you need to do here. Again, pay attention, this is a vector. So for each of them, you are doing the modifications to it. So how do you get this delta W subscript J superscript R whole bar is equal to minus mu into, very good, dou J by dou W J R bar. This should not surprise you. This is something we have done with a single neuron there. Gradient descent only is what I am following here. You go in the direction, a negative direction to where your gradient is increasing, you come in the decreasing direction, there is a negative sign. The rate at which you are going to take steps is given by minus mu. Of course, the steps, you are scaling the derivative value by the step. Your final function, cost function is J. J is a function of this W bar. And what is your variable here? What is it that you are adjusting here? It is the W. So delta W J R bar is equal to here minus mu into dou J by dou W J R bar. Clear so far? Okay, right. So, well, how could this J be? What would be that function? How can we define that function? One possibility is this J equal to, now also consider a case where you have n samples. Now, for all these n samples, you want to compute an error function and sum them that error function. Okay, this we again told two variants earlier while we are talking about the single neuron model. What were that? Other is every pair of xi and yi, you look at the input, you give output and do the update. But more robust one, although it has its own advantages and disadvantages, is you sum over all selected set of samples. Okay, so let me write it as I equal to 0 to n, I equal to 0 to n, some error function that I am going to compute for that pair of x of I comma y of I. See, I made a conscious switch from earlier ith set x subscript I we were using, but now like your hostel rooms, there is a space constraint here. This cannot set subscripts we are already using for jk and superscript for the layer. So we made it as an index here. This is I is telling you the ith sample. Okay, so error computed for an ith sample, and of course this error you could compute it in different ways. For example, one possible way of computing this error is equal to, I'll first write and then it will be very obvious to you. M is varying from 1 to k subscript L times k subscript L times some function em square. Okay, I purposefully am writing it as em square, although I could have avoided it. You will see the reason. So some error square you are taking, and where you are doing it, this error, where do you compute? You know ground truth only at the end, you don't know in between. So you are computing the error at the Lth layer. Last layer is the layer number L. As I said, we are not restricting ourselves to just a single neuron there. There are n number of neurons there, KL number of neurons. I should consciously and correctly use, I cannot call n is number of samples there. K subscript L are there. So I go through each neuron, and at each neuron, I know what is the output to expect, and I compare that with what is the output I got. So that difference square I take. Okay, and this would be my error. And I'm sure you could tell me why I have taken 1/2 here. You need to take derivatives there. There I don't want to have half, so I took 2 there, so I took half here. Other than that, there is no extraordinary reason to put 1/2 here. Okay. Which I? Very good. So this I compute for each this em square I will write, then it will be clear. So let me write this expression also. Em square of I, that is computing what it is, for example, is 1 by 2 into m is varying from 1 to k subscript L ym of I minus y subscript m of I whole square. Look at that. So this is something that you would expect ideally the output, okay, at the mth layer. So you are very, see, you have this vectors, the scalars have to be absolutely clear to you. You are giving just a set of, you have one set here at the very beginning one, you will be giving x1 feature vectors could be x1, x2, x3 whole, that's an x bar there. That once you give it, you get a y bar there. These two can be of different sizes, correct, depending on the outputs you are expecting. Then you got something out of your network. There are KL neurons in the output layer. So you will get KL outputs. You also know what to expect from there. You are subtracting at each node the respective value that you got from the expected value, from the actual value, which you know from the training set, squaring it, and half you just a constant adding there. Is this clear? This cost function has to be clear. Otherwise, I don't mind explaining it, trying to explain it in a slightly different way. Which one? This. Okay. I is nothing but number of samples, number of training samples. I have n. Okay. So my I is nothing but that varies over 1 to n here. Sorry. So I have a set of samples in my training data set. This is the input and this is the output. So I have n such samples. That is what I am indicating, this error I am computing for each sample. Yes, it can be a vector. That is what. So when I say, isn't it? It's the earlier, that's a feature vector basically. Correct. And output also, we are keeping it general that it can also be a vector. Otherwise, this will become 1 essentially. This, whichever m equal, which not here, but yeah, that will be a simple one. You are calculating it at the output layer because that is the only way you see. You expect some output there. You have built a neural network. You know only ground truth at the end. So this is the overall error of your system, you can say. Is it not? It is at the output layer. The error you are calculating is at the output layer, but that is a result of your entire network because everything is getting propagated. Clear? Any other questions? Do not hesitate if something is not clear. Is that fine? Okay, good. So essentially, this you need to compute for dou E of I by dou W J bar. You need to compute for each sample set and then you need to sum it over, right? That's what you need to do here. So the next step for you is to compute dou E of I by dou W J R bar. This is what you need to compute. This again, look at here, there is an output here and there is an output here. These two are different. So you need to do till this versus till this. There is no other way. Well, if you see here, this could be the output Y that you are getting as a result of this. I could call this again as Y. Okay, output of R minus 1th layer here, is it not? So I call it as, let me somewhere write it, Y of R minus 1th layer could be from a kth neuron. Y of R minus 1 subscript K I have kept. Okay, again, for each neuron, is it a scalar or vector? It's a scalar. Okay, I'm happy that None of you had told a vector. That's right. Good. This is just a scalar at every vector. Just that we were combining everything together. That happened to be a vector. But otherwise, each neuron output is just one point, right? In that multidimensional space. This is one thing you have. And so we will call this. So basically, I could, in a similar line, I could write here this, let's say, is output. Assume that k again could vary to any of them. So here also, if I, let me, just to avoid that, let me call it as a jth neuron. Here I am looking at some kth neuron. Here I am looking at, this is in the layer R here. Okay, this is R minus 1. So this has to be R here. And this, let me call it as, what I am getting is V. Again, this V could very much depend on the neuron number and also the layer number, of course. Okay, this is nothing but f of this is activation function we have discussed yesterday. F of x is 1 by 1 plus exponential of minus ax, you could do. Okay, that will give you this V. So f of vkl would give you vk, or yeah, I should call it R, right? I should not already come to the last layer. vkr equal to ykr. Clear? Now, can you tell me now how I could write this now? Chain rule, you use that. Do E of I by the weights coming here. See, this is WJR. Okay, so you consider a neuron here. The weights are coming from here. So this, you write it as derivative of this and the derivative of the other thing. So just to ensure, let me first write and then explain. Do Vj superscript R of I into do Vj superscript R of I by do W bar times J times R. Hope it is now clear with that explanation. All we are doing now is this error. First, you are looking at WJR, you have to do. You are doing it VJR, okay, followed by VJR by do WJR. Is that clear? So you are doing it in 2 steps now. You all know the chain rule, right? So this WJ is in fact, before that, before you get the weights, there is a V standing here. Correct? This V is there and then the weights are there. Here also the same thing here. So the way we are writing here is, hope just I wanted to ensure I wrote it correctly. Right. So again, be clear. This is again a vector, scalar only. V is nothing, is not a vector, right? It's just one output that you got before applying your activation function. Before applying your, where is the activation function? Here. Okay. Right. You know, VJR you can express in terms of W, is it not? What is my VJR? VJR of I, if you want it, okay, is nothing but, let me, rather than this, let me write it this way. Summation of K is varying from 0 to K, yeah, K subscript R minus 1 into W J K R into Y K R minus 1 of I. I'll write it and then I'll take you there. Okay. just for sake of consistency, let me write instead of J here K, and instead of K here J, so that there won't be any inconsistency in notation. Pay attention here. See, these are YK R-1. These are the ones which are coming that kth node. Right. This is at kth node I am getting, correct? VKR at a kth node. How do I get that? This summation is what I am trying to get, correct? This would be, ignore for a moment k equal to 0. You have now for a kth node I am getting, okay, I go through all j nodes varying from, okay, j node. So this j is representing this, correct? This I would go from 1 to kr minus 1. J I want to have this itself. This I want it as k. Okay. So here I want to call it as j and that as k. I think I forgot to change this and suddenly I'm seeing jk there. Okay. Look at now. Hope you are clear. Pay your attention. This is the output I am looking at. How do I get? I have here outputs coming from r minus 1th layer or y. Y are the y r minus 1 layer. So that's why I have y r minus 1 layer. And how many do I have here? The neurons in that are varying from 0 to kr minus 1. That is what I have taken here. And the weights for that corresponding one are to the jth node coming from the kth layer there in that. I am putting it one more k here. Okay. And these are the weights for this rth layer neuron itself. So I am putting their r there. Okay. Is that clear? And of course, there is W naught here. So what I implicitly meant here is Y0 of R minus 1 of I is equal to 1. That's what I essentially, you remember the way we augmented it to just avoid that additional bias term. So you take that, so that is taking bias Wj 0 of R is essentially your W naught there, bias function. This Y for that is 1, that's all. This one, huh? Yeah. See, the weights are coming. So see, what is it that I am looking at is output here. Okay. So the output here is nothing but double. So here the corresponding one I call, let's say here W, the weight W. This is a J neuron here. I call it as J, and coming from K, that is K, and this is corresponding to the rth layer power R. Those are the weights there. Okay. And then anyway, for 0, there is nothing there. Means there is a bias here. In fact, if you want, I could write this. That would have been Wj0R, right? So if I make Y0 of R minus 1 equal to 1, I will get the same thing. Clear? Right. You work it out then. What is that? How do I get this? Now VJR is there. So I will go to this calculation of this. Okay. I wrote it as if it is a omega, but that is a W only. So you do that now. Do VJR of I over do WJR bar. What would be that? You are taking with respect to this one. Okay. This could take all these values. So first element, second element, third element, those are the ones which you are showing there. So what will be those values here? This is again a gradient like stuff. What is the first element of this? What is the value of the first element? 1, correct. Because anyway, you just expand this, that is 1. Good. Second element, y1 r minus 1 of I, right? Second element, y2 r minus 1 of I, so on. Last element, y k is going y k subscript r minus 1 of r minus 1 of I. Okay, it looks like some stranger to you in the first look, but it is nothing but these are all put together with just one added to that. Nothing else is happening here. So this is nothing but I let me call y cap y bar of r minus 1 of I. See, this is nothing but you concatenate all of them as vector, put one also on top of it, and that is this, nothing else. Your known friend just one layer before he was there. Just he came now wearing a hat one, nothing else has happened here. You just expand this. If this is not clear, always resort to expanding and looking at it. This is nothing but w, j, k is for a given j. So j0, j1, j2, j3, j4 and so on, right? Then as I mentioned, this wj is having all the elements there. You are taking with respect to j1, j2, j. See the elements, what is this wj here? Wj bar is nothing but wj1, wj2, wj whatever, that how many are there? Kr minus 1 are there. K subscript r minus 1 are there. You consider here also this is anyway 0, first one is not there. This is what it is happening. Dou E of I with respect to dou Vj r of I, this is a little bit tricky. Okay, so let us for the time being call it as delta j of r. Okay, now I'm trying to follow the same notation as used in the textbook. I am not diverting anywhere. The reason being, even if something is not clear to you now or later point of time you realize that something is not clear, you have a proper reference. I'm not messing up or mixing from multiple sources. So please go through the Theodotus textbook. I am very religiously following that book. So you will find notations and everything the same. I'm not changing or bringing any of mine here because that's already is in a good shape. Okay, so let me write at least this equation now. What's the equation that you got here now? Let me, for the time being, call dou E of I by dou Vj subscript r of I as delta jr of I. All I have written is this one, nothing else. Okay, don't think I have this. I'm considering it as delta jr of I. Notice here, this will be a single constant. It won't be a vector. Is it not? Look at Vj is a single value. E is a single value at the end. So this is not a scalar. So that's why I'm not keeping any bar here. It is, there is some value there I would be getting eventually. And if I that multiplied with my y cap of r minus 1 I would give me delta double. This will give me, what does that give me? This E of I have it. I need to sum over all n samples the error that I have got there, and that will that if I do so, this derivative I take inside and take sum, I will essentially get this term there, is it not? So my where I will stop here is at this point, delta w j subscript r bar is equal to minus mu into my j is nothing but summation over I equal to 1 to n E of I, which is nothing but y bar of r minus 1 times I. I equal to 1 to n into delta j subscript r of I into, then I should write y bar coming from the r minus 1th layer for ith sample. Okay, while the derivation is hectic, interpretation of your final equation is very comfortable. Of course, we packaged all the difficulties into this term right now. We will try to open that box in the next class. So again, come prepared with a good sleep before that night. Okay, I will also ensure that I will have a good sleep before that. Otherwise, I will also mess up things too much. Right. See what has happened here. The step you are taking here to move from its previous weights to the new weights at a given neuron is nothing but you are taking all of those inputs here, right? And of course, mu is some multiplication. This taking is all those weights here is these weights, multiplying it with some weighing factor, which we are yet to compute. And that will drive you your delta W. Okay, this equation understanding and remembering is very simple. That's why I told on a coffee table discussions of backward propagation, this back propagation is pretty easy. Even equation you could say and do it. But again, it is okay. Every time you might not remember the whole stuff. But if somebody asks you, have you studied machine learning and what is your favorite topic? You tell them that back propagation is my favorite topic. You tell to the interviewer. He will not ask you any more questions. Okay. Even I cannot ask you if I were in the interview unless I come prepared once referring back to it. Okay. So this is, but again, this interpretation is not that difficult. This has to stay with you. This you can refer and do it. So when you read it, this has to be clear to you. But what should stay with you is this equation. All it is telling you is at this a given neuron, I want to adjust its weights. How should I do? You take all these feeds that you are getting from all these neurons. The outputs of those neurons are Y from the previous layer. You have some weighing factor coming here. This is still a black box. It will take us inside and we cannot come out if we are not in a good shape. So that weight we will see later anyways. Of course, then there is a mu here, minus mu. That is, after all, telling you with what fraction of that or a factor of that we should change your weights. Yeah, same interpretation of single neuron applies here. If your mu is very high, that means you may miss it and go. If you have a very broad kind of a function there, which has a minimum or a long duration, taking big steps is okay. Okay, that itself with the road itself is a 20 feet road. You should not jump too much. Okay, then you reduce this out. And that's how you are getting this. And again, where is the final error in the whole process? Because that's from where everything has to come here, right? Where is the error? Yeah, the devil is now in delta. We will handle this devil in the next class. We will see that. Okay. So any questions? So I request you all to please go through the Theodoros' textbook. I think I'm sure all of you, if not hard copies, have soft copies. As I said, every notation is followed as per it. So please go through it. Okay. This this is kind of a very important component. Back propagation is a very, very important component which you should master. If you have done any course related to neural networks, machine learning, this has to be, you should be mastering it. But again, I myself don't remember all the steps, but when you see it, you should be able to do it and understand every bit of it. Because tomorrow, what could happen is you should not remain as a simple practitioner of machine learning. What I mean by practitioner, I think in the beginning classes I was mentioning, is that you only know, you set number n equal to, you set the number of neurons, in that there is some tool and you just wait at the output and what is coming out. That's what you are seeing. And if I tell you that, look, I have a better new function to estimate the error, unless that software whichever you are using gives you that error function, you are handicapped. You cannot do anything just other than waiting at the outside door. And this is a new you have probably, for a specific application, you are working in your computer, in a company where you are working, or in your research, you may figure out that, look, I don't want to do mean square error. There is something that really makes sense to me. The whole derivation for this is indeed dependent on the kind of error function you are using. So unless if you understand it and don't remember each step of it, it's fine. You can keep that and see how this is done for that, and you should be able to do. And this is what distinguishes somebody who learns machine learning in 10 days, crash course. If you do that, you will get crashed unless you have this whole background of the mathematics and the way you arrive at that. Okay, with that note, I'll stop here.